moles we find, we just divide it by a liter to get the molarity again when we want to put it into the Henderson-Hasselbalch, because the Henderson-Hasselbalch uses the concentration of the acid and the base. Okay, so keep that in mind, because that's going to add a layer of calculations to some of the things we're going to do, where in this problem it does not, simply because it's already at 1 liter. All right, does that make sense? Okay, so I think we did this thing here, and this is prior to putting in the solid NaOH. We had the 1 to 0.1. Remember this, the closer this ratio is, the better. We discussed that. Also, the closer pKa is to the pH, the better. And that way it doesn't move as much and it stays around the pH you want. I had a full discussion on that last week, right? Okay.
We finished up the table and everything.
So then we went through all of this, and then example 2 was just adding the...
We didn't do that one.
So here, okay. So here, we're going to calculate the pH of a solution in example 1 after adding this stuff to it. Now, the key here is it's mentioning that we're putting in 2.5 mils of the strong acid. That's what's going to adjust the pH, right? We have a pH buffer system, and we're going to use 275 mils of that original buffer, which was in question 1. Does that make sense? And then we're adding 2.5 mils of the 1.0 molar HCl. So what happened in this problem, and where's the uniqueness compared to the last problem, or problem number 1 and now example 2? The volume, right? And what we're putting in. The first time we put in a strong base, this time we're putting in a strong acid. Last time we used, and I just got done saying this, 1 liter. Everything was wrapped up in 1 liter. So the concentration was whatever divided in moles divided by the 1 liter. Same, the moles and the molarity were the same in that case. And I wanted to point that out so it didn't become confusing. Because now the volume is 275 plus 2.5. That's your total volume after you add everything together. A lot of these questions are going to ask you, what do you add? How much are you adding when you take one thing and another thing and you mix them? But the concentration is the mixture, is the total volume. The moles of whatever it is in the total mixture. And that's the molarity, the concentration that you're going to put in when you're determining the new pH based off of a buffer system using the Henderson-Hasselbalch equation. Okay, and that's got to be really, really clear, because what happens here is you're going to end up thinking that the moles are whatever they are, and then you want to use that into the concentration for the Henderson-Hasselbalch, and it doesn't work because it's not the molarity. It's just the moles, that's an amount, right? You could equate the moles to a mass by using the molar mass as well, which you might start off with a mass instead of moles and then have to figure out stuff, and we'll see what happens as we get further on. Okay, so here's, and anybody that's had me, I've said this many times, I'm laying out some steps, but you don't have to think about it in these steps. This is just to guide you in the newness of the material. So you get a chance to say, okay, if I'm not sure of something, I'll just follow the steps. But if you already know how to do it and you're comfortable, you'll just automatically do these steps. You're not going to think about them this way, right? So here, step 1, calculate. In this case, millimole. Doesn't really matter if you calculate millimole or mole. A lot of it depends on what you're using. And in this case, since you're using milliliter, it's pretty easy to calculate the millimole and then divide the millimole by the milliliter in order to get your molarity.
So when you're calculating millimole for the ice tables, why before were we using molarity and why are we now using moles?
Why were we using
like ice charts for last chapter, we use molarity, but then for this one we're using moles. Is there a difference, or can we?
I'm trying to recall what you're
Because like for last chapter we used
You're just
molarity.
using the concentration of the species with molarity, and now we're using moles.
We're using millimoles.
It's the same.
I thought we used, did we
It's the
use
same.
millimole last time?
No, we used
No, we use molarity
We use
moles, but
molarity
But it's still the
instead
same
of moles.
ratio. Like,
it's still the same. It's just you're not doing the division of the
You're adding,
1,000.
like,
Is it because
You're
the
putting these
concentrations
things
are less?
together here. So you're starting with one thing and you're determining how much left in terms of the moles of another.
So we would get the wrong answer if we use molarity
Well, you
in the
can't.
ice charts.
You can't use molarity necessarily here, can you? Because you're going to have a different molarity.
Yeah.
You're going to have your, let me
Is it because
see,
it's a one-way
pH
reaction?
position, millimolar. You have your moles here, but you don't know your molarity here, and you have a different volume in both. In the other ones, I think you were already set with your volume. Is that not true? You didn't have to adjust your volume before, did you?
no, in the last chapter.
No, here you do.
Okay.
the volume here, you're putting in this amount and you're putting that volume of that amount in.
Okay.
Here you're putting this amount and you
So
don't know
because
your,
of the difference in volume. That's
well, the volume is gonna change your molarity, right?
Yeah.
So if you use the volume of the original, then, and you don't know the moles at the end of the equilibrium, then how would you determine what your molarity was?
Okay.
You'll have the final volume,
Okay.
so maybe that's what you're
Yeah,
asking?
yeah, that's what I-
I'm not 100% sure of the
No, that-
equation that you're using, but maybe that's the distinction that you're trying to make.
Right, okay.
Okay? Okay. So here you do use your moles. This is involved before the addition of whatever you have. So you haven't actually mixed them yet. Then you're going to calculate the millimoles after the mixture. And what's actually happening here? So when we're talking about moles and we're looking at stoichiometry, we're looking at the balanced chemical equation, and we're saying I start with this, I now put in something that's going to take some of that away from you, right? And that's going to change the mole ratio in the Henderson-Hasselbalch equation, because now when I put that over whatever the total volume is to get my molarity, I'm going to have a different pH at the end now.
Right.
Right? It's going to adjust it. You see? Okay, good. So I'm getting the impression that you're understanding what's going on here. And that's really important because this step here is just sort of a similar step to what you've already done. But it is an extra step before you use the Henderson-Hasselbalch, which up to this point you just plug in because you were given the concentrations. But now you're going to add something to those things. You're going to mix them first, and you're going to add something to it. And in that addition of something, it's going to adjust what those concentrations are going to be in the Henderson-Hasselbalch, and therefore it should adjust the pH accordingly. So if I'm putting in an acid, I'm going to take away the conjugate base of a weak acid conjugate base buffers system, and what should happen to the pH? To go down or up. And then how much down or up should it go? And that's what we're going to start looking at from here on out. So at least this part of the chapter. So we're going to calculate the millimoles after the addition. Here we're going to calculate the initial concentration of the species before the equilibrium, and then we'll calculate the pH. And how are we going to do this? Henderson-Hasselbalch generally? Okay. So let's start with the first part. Millimoles of HCl. Using millimoles simply because I use milliliters. If I started with liters, I'd probably just figure out how many moles I have, right? The idea of using the milliliter means that I could just put this in and find the millimoles. Just to make this really clear so I don't have to go back to this, if I have 17 molar, that's equal to 17 mole per liter, okay? Which is also equal to 17 millimole per milliliter.
Right.
Okay, it's a real simple thing, but sometimes people get caught. So when I'm talking about if I'm using, I want to get this out of this and get the amount in terms of mole, and I have milliliters, then I would just use this and I get my millimole. And then when I get my concentration back, when I add together my total volume, I just use the milliliters again to get back to my concentration, which is molarity. But if I'm starting with liter, then I would probably want, this would be liter, I wouldn't use the milli part. And now I just cancel those out, and now I'm dealing with mole. Millimole, mole doesn't really matter. The point is that's just an easier way to quickly assess what the difference in amount in terms of moles. Okay, so don't get confused by the milli thing. I'm starting with 2.5 mils of the HCl. I'm putting it in the 1.0 mole per liter, so that should say millimole per milliliter, as I just described here to make that easy. Okay, and that gives me 2.5 millimole. That's the amount of the HCl that I'm putting in. And remember, the HCl is the strong acid. That's going to be neutralized by the weak acid conjugate base buffer system, which means that it's going to occupy some of the weak acid's conjugate base, right? That's what's going to attach to the hydrogen coming off here
Make water
and neutralize it. But it's also now going to pull down the conjugate base amount
right.
compared to the weak acid. And then when I put that into the Henderson-Hasselbalch equation, now you're going to have a different pH.
Lower the pH.
Right. Does that make sense? Now, if I used all of the conjugate base up here and still had some extra acid, well, now my buffer system was bad, clearly, because I didn't have enough of it. Right? Maybe it was too dilute. And we'll talk about dilution as well in a second.
Okay.
Okay, so here are my millimoles of this is my weak acid, acetic acid, and I think, so I'm starting with 275 mils of a 0.1 molar solution, which gives me 27.5 millimole. That's how much of the weak acid I have, okay? And the conjugate base of the weak acid is the same thing because I put this all in together. I'm using, just to make sure this is clear, these are coming from example 1, okay? Just so in case anybody, I don't want anybody to get lost in this. This is just the buffer system set up in example 1, except for now I think I had a liter of that, I'm only taking 275 milliliters of that out. Okay, so I had a stock solution and I'm taking, of a liter, I pull out 275 milliliters and I put it over here. And then I put this 2.5 mils of this concentration of HCl into that. That's all I'm doing. Okay, just to make that clear. So then what's my equation? What's my chemical equation here? Okay. So this is going to attach to this.
Right.
Right, okay, good. So here we go. So, okay.
That kind of like represents the HCl.
The HCl is essentially an acid.
Yeah.
I could represent it any way I want. It's a strong acid, that's important. Okay, so here it's just being represented like this. Okay, I could also put H plus, or I could have just put the H plus from the HCl, right? That's what this is representing. It's binding to the conjugate base of the weak acid, and this is what you're forming, and this is also off. This should be C2H3O2. That looks like it's just, okay. Make sure that you put that up. Is it in your notes? Okay?
Yeah, it's on the.
Okay, it's just not right. Okay, good. Okay. So now, I'm starting with this amount of the acid, and I have this amount of the conjugate base. So I also have this amount of the
Acid.
weak acid, right?
No, it goes only.
Now, this is going to be neutralized by the same, all of this should presumably be neutralized since I have so much of this
Right.
here. So I lose the 2.5 here, getting 0. I subtract the 2.5 of this that's being used up to form this. So this drops to 25. This goes up because this moved up. This was added to, this 2.5 was added to that to gain 2.5 millimole more of this. So I end up with 30 millimole here. So what does this indicate here?
Does that lower the pH?
Those are my amounts
Right.
of the acid, the weak acid and the conjugate
Conjugate
base
and the
after
acid
the
part.
addition of the HCl.
So this goes into your equation.
Those are my amounts. Dieter?
Why is the conjugate base the same as the original acid? Because wouldn't it be at equilibrium since it's a weak acid?
Sorry, say that again?
Why is the conjugate base concentration, or the moles, the same as the original acid? Wouldn't it be at
That was what we saw in example 1.
Mm-hmm.
Go back to example 1, and that's the ratio setup.
Right. But from the last chapter, it would be, from what we know, it would be at equilibrium, so not all of it would disassociate to the conjugate base, right? Or to the acid.
It's what you have at the beginning before the equilibrium.
Maybe I'm not understanding what you're asking. This is what you start with. Before you add this, you're starting with these two things here. So now, right here, you figured this out here. Because in the example 1, you had 1 liter of a 0.1 mole solution that had this and this in it. Is that not true?
Never mind. Yeah, because it was stated in the question. Yeah, never mind.
Is that okay now?
Yeah.
Okay, I'm missing I'm not fully understanding some of your guys' questions this morning, I guess. That's probably me, not you, so don't worry about it, but hopefully we can solve them either way. So are you okay here?
Yeah.
So this is just starting and starting. Now, as this thing goes this way, it's going one way. By the way, you notice the arrow's one way here. This is not an equilibrium, right? That's also really important. What's that?
Then why are you using
Of the strong acid?
It's
Because
the
it's
initial change
all
in
going.
Not.
I think that was.
Yeah, this would be,
Initial.
and this is the initial amount. This is the change in amount. This is the end amount,
It's like,
not the equilibrium amount, the end amount.
I think that's what my question was, like, that's what I was
But
thinking.
maybe, was that also part of yours?
Yeah.
Is that we're neutralizing something, so we're going all the way to the end here.
Yeah, so
The
it's not
HDL.
technically an ice chart
Right.
then.
Well, ICE, it's but a different,
Oh,
the
okay.
end point
That's
is
okay.
different than the equilibrium point.
That's okay.
Well, they're both the end points,
Just the
but this
addition.
end is representing a completion of the reaction, where the other end is representing an equilibrium
Okay.
between the two things
Right.
that you're starting with
No,
and
that
you're
makes
ending with.
sense. Okay.
Does that help both?
No, yeah, that totally.
Okay, okay, maybe I should have pointed, I didn't. See, these are the things I need help with sometimes from you guys, right? Because these things seem intuitive to me, but hearing it for the first time, I doubt it was intuitive to me, but at this point it is. So as you guys help out and you're not certain of something, let me know and I can help, guide you through it. Okay, so keep that in mind. And once again, when I'm developing this system here, which is what Dieter asked about initially, that is an equilibrium, right? Now I'm saying I'm putting an acid or a base, strong acid or strong base in, just like if I put a strong acid or strong base into water, it all dissociates, right? This case, this is all going to dissociate, and it's just going to bind and form through this buffer system. That's all I'm saying. This wouldn't be an endpoint if I didn't have enough of this to balance that out. Right? Then I'd have some of this left over and my pH would jump way down, right? My H3O plus concentration would jump way up, right? Make sure that that's clear. Is that okay? Does everybody get what I'm saying? Okay, so all you're doing here is determining how much either the conjugate base or the weak acid is neutralizing, in this case, the acid put in. So you're just adjusting these amounts here. Now, once I have these final amounts, I now need to convert these back into what? Into molarity, into concentration. So how much did I put in? What's my total volume here?
275 was a 2.5.
This right here. And I put the line there because it's 3 sig fig things. So I take this divided by this, and I get 0.108 molar. That's the concentration left over from the weak acid in the weak acid conjugate base buffer system after the addition of the strong acid. Okay. And the same thing here. Then this is going to go up or down. It went down, right? Okay, so 25 divided by 277, this is going to give me 0.901 molar. So in the notes, what was the pH of the buffer system prior to adding the HCl?
4.83.
4.83. So now I'm going to use the Henderson-Hasselbalch with those calculated concentrations here, and I get 4.66. So what happened?
Went down.
pH went down
Which
Right.
increased in the denominator.
because of the adjustment here of the ratio of the base to the conjugate base to the weak acid. Does that make sense? What's happening here? Okay. And did it go down a lot?
No.
No. Now, what would have happened if I just put that directly into water? It would go down a lot, right? And that's exactly how the buffer system is operating. And now you guys have the tools to figure out specifically how much of an adjustment your pH will be if you wanted to add an acid or base to a buffer system. And it presumably would go to much, much less in its alteration relative to if you just put it in water.
So for a buffer, ideally it should be like within a 10.
Tenfold?
Yeah, it should be the acid conjugate base, or the conjugate should be within 10. 10 of each other.
This ratio.
Yeah, exactly.
Yeah. Overall, you want the pKa as close to the pH as possible. And, but you could adjust it like up one, down one. So if you want 5 here, you don't want it to be any lower than 4 or any higher than 6. Ideally, it's right at 5, but that's, kind of hard to get those exact like that. That would just be, if I had this at 5 and I had a 1-to-1 ratio here, then I have the smallest change when I put in an acid or base, depending on which conjugate system I have for the buffer, and I'll have the smallest change, and also I'm assuming that that's the pH that I want at the end, right? So if you, but there are a variety of things. Let me rephrase this, I guess, to wrap up the kind of intellectual idea here. Let's say I want to use a buffer system, I want a final pH of 5. What I'm saying is then, this number here, the pK, I wouldn't want any lower than 4 or any higher than 6, but ideally it's 5.
Right.
Okay? Additionally, this ratio would be perfect at a 1-to-1, with enough of it to completely neutralize any acid or base that I put in. Because that will give me my smallest overall change in pH is close to the pH that I want, which is 5. Now, if I was really crafty, I could think of a little bit better way to do it. If I wanted 5 and I wanted to put in, let's say, a strong acid, then maybe I want to make this or this ratio so that it's 5.2 or 5.3, and by the time I put in that strong acid, I've now dropped this down to 5.0. Right? You could think of it that way, but the easiest way to think about it is, hey, if I'm close enough to where I want here, and all these things are right, it's only going to go down a little bit, I'm going to be right at where I want to begin with anyways.
The whole thing?
Right, 4.94 versus 5 or whatever is close enough. Okay. Now, this is something I did go over already, so I'll just briefly talk about this. Or maybe I just did. You have two buffers composed of, you have this weak acid and its conjugate base with a pK of 5. But differing acid conjugate ratios. Okay, so what they want to show you here is that, and this is what Harash just asked actually. The ratio here, the best ratio is 1, and I've said that over and over. Okay. If I go 10 down or 10 up, that would be the minimum and maximum range of the weak acid conjugate base buffer system, or weak base conjugate acid, of course, system ratio that I want. So ideally it's 1. I don't want to go less than 0.1. I really don't want to go more than 1. Or I guess
1.1?
Actually it usually goes 10 both ways. So this would be 0.1 and 10.
Okay.
Right? 1 is ideal. That's it. Okay, so now I guess we're going to just take a look at that. So we're going to look at the two examples there. Okay, let me, since they're not really saying it here.
Means like 0.1 and...
The ratio of the buffer system, okay, here over here, should be as close to 1 as possible. 0.1 is sort of the low end,
1.9.
10 is sort of the high end.
1.9?
Does that make sense? That's all it's saying.
Wouldn't it be 1.9?
You're just going 10 down, 10 up, tenfold, the same thing we just talked about.
Right, 1.9.
What?
It will be the tenfold of 1 will be 2, no?
1.9 is the lowest you would go because you're only taking out 0.10.
What's 10 times 1?
I see what you're saying.
What's 1 divided by 10?
Right.
It's just a tenfold difference up and down. That's all I'm saying.
Okay.
I'm not saying any more than that.
Yeah.
Right? Anything in between is okay either way.
Okay.
I think you just gave me a number in between, which is fine.
Yeah.
That would fit within the buffer effectiveness range is what I'm calling it.
Correct.
Okay? That's all. And that's the ratio. Nothing more than that. The ratio referencing through the Henderson-Hasselbalch equation. Because what I'm saying is that that buffer amount is not going to change the overall amount as much. But what I will show you is that if you have 1 or 0.1, or had I gone to 10, that you do get a greater pH change from here and here than you get from there, which is non-ideal. It's more ideal to get the smallest change possible, which is why this number is the best number within it. Okay? So here's buffer A, and what are they defining as buffer A? It's a 1-to-1 ratio. Okay? So if I do the 1-to-1 ratio, and then I say I'm going to add some strong base, that base I'm going to put 0.010. This is just a demonstration to show you the pH change based on the ratio of the conjugate base to the weak acid, or inversely, the buffer system. So this is my 1-to-1, which is what I'm saying here that I prefer. And when I do that, and then I'm just putting in something that can be eaten up here, the OH here, it's gonna bind to this, I'm gonna get this, I'm gonna lose 0.10 here, I'm gonna get 0.09, I'm gonna gain 0.1 here, 0.01, I'm gonna get 0.11. I put this in, this is my conjugate base, this is my weak acid, and starting with a pK of 5, I end up with 5.09 for my pH. Okay. So my original at 1 to 1, what is log of 1 to 1 again?
0.
0. So what was the original pH?
5.
5. Okay, everybody recognize that? That's important. So 5 went to 5.09, so my percent change is 1.8% by putting in that weak base with the 1-to-1 ratio. Now I'm going to do the same thing, but I'm going to start with a 0.1 ratio, which is the second. I'm going to put the same amount of base in, and we're going to see what that change in pH is over here, and therefore the percentage of that change. And we'll compare them to see which one's more ideal. Right? Okay, so here I'm going to do the same thing, but now I'm starting with the 0.2 and 0.118. I'm going to add this. That's going to adjust these things. I'm going to get this ratio now. Once again, I started with a pH of 5. And now I'm down to 4.25. And that percent change is a 5% change. Once again, a lot better than if I had used just water without any buffer system, but nowhere near as effective as the 1-to-1 ratio, which is the point. Right? So this takes me here. This has a greater change in the pH. And once again, though, so this is kind of an important part here. Not so much for this class, because what am I doing here? I'm just trying to show you what the best way, if you had everything aligned, to do. But what was the first thing I just got done doing right after before I started this, right after I wrote up here? Was that you may want a greater change. If your pH, if I want a pH closer to 4.25, and I don't have any buffer or any buffer system that doesn't have a pKa lower than this, then I might want this change in order to get down to the pH that I actually want. Even if it's not ideal under an ideal condition, because you only have available whatever you have in lab or you can purchase or whatever else. So you may not have a buffer system that takes you to the pH that you want with the pKa, so you may not want to do a 1-to-1 ratio. If you want to bring it down some, a little more than the 1-to-1, so if you recall, the 1-to-1 ratio did this. It went to 5.09 here, right? That's a 1.8 change. This one goes to 4.25, it goes to 5%. I may have wanted this 5% change. I may want a 7% change based on whatever I'm starting with. So if you're doing your own research in a lab, you may want to make an adjustment that goes further outside what's ideal, because you don't have an ideal starting buffer system for what you want. Ideal is only relative, right? So keep that in mind. What we generally do in these slides and with the book, this is following the book, is just to point out that you're making an assumption you already have all the perfect components already to start with. And if you do, these are the minor changes you want to make, because this was what will make it optimal. But you may not have those. So then in order to make it optimal, you may have to make these kinds of adjustments to end up with what you want in terms of the pH. Does that make sense? Okay, I want to make that clear. Once again, this is the book, and this is just stating this is always going to be optimal, but that's not anywhere near the case most of the time. Go ahead.
So in a case like that, you would choose the conjugate acid-base pair that have the closest pKa to the pH, and then make adjustments to the log.
Ideally, yeah. And then make adjustments to the ratio, but after, yeah, absolutely. You still want to be within the range of the pKa, because you don't want to get too out of whack from this idea here, because what's going to happen, you're going to end up with very little of 1 at the end, and that's going to increase maybe too much the pH one way or another.
One of the lab questions was about that. It's like, given the pH, choose the best conjugate acid-base pair. So you choose the one closest to
the pKa closest to the pH, yes.
Exactly. But if it was a number where a pair wouldn't match match exactly, you have to make other adjustments.
Then the adjustments would be made here.
Yeah.
Absolutely, the ratio. But once again, you don't want to get too far outside of this realm, because when you do that, you may have to at times. But then it's not going to always, you see, going tenfold went from 1.6 or 8 or whatever to 5. You know, if I go 20-fold, that may not just jump to 10, that may jump to a 50% change or something. Yeah, so you got to be careful in that. And that also will relate to the total amount that you're using of both these two things, not just the ratio of them. Right? So if I wanted to go further out and I use this same amount, let's say I'm putting 0.1 in here, well, now I'm going to have a bigger problem. I may want to increase this to 1.8 and 2.0 in order to keep those two that same ratio to get that change, because I'm using too much of, I'm getting rid of too much of either the weak acid or the conjugate base, or inversely weak base conjugate acid, depending on what I'm doing. Does that make sense? So the amount matters and the ratio matters in both cases.
Question, in a lab, how would you determine how much, or what determines how much of the buffer system you actually make? And it depends on how much of the strong base.
How much of the strong acid or base are you putting in? It's going to matter the total amount.
Right.
And the ratio will matter to what your expectations are that you'll get as a result of that. Because you can anticipate, right? This is not you don't have to actually do this to figure this out.
You can do it in the lab.
You just like this.
Right.
So if I have a certain amount of this and a certain amount of this in some ratio, and I want to put in a certain amount here, then I could do this process and see what I get, and I could make adjustments here by adding some of these things, or changing the ratio, adding this back, and then seeing how it adjusts to this.
Okay.
I could literally just do that on paper,
Right.
right? Until I end up getting something closer to what I want as my final pH.
Unexpected value.
Absolutely. Right. So the first thing is you got to make sure that you're not using too much of either one. And so you have enough of this and this to compensate for the adjustment of whatever you're adding. Then you're looking at the ratio and how that ratio will overall affect the change in the pH as a result.
Thank you.
Does that make sense?
Yeah.
Okay, so here we're seeing that you get a much greater change as I go tenfold down from that 1-to-1 ratio. Okay. And that we'll just call buffer effectiveness, and we'll just say here that the concentrations of acid conjugate base, or that should be weak acid or weak base conjugate acid. I'm not going to keep saying that every time I say weak acid and conjugate base. I mean both. Either buffer system, okay? Make that easier. I think I called it buffer system 1 and 2. I could just say just a buffer system. That just implies you're dealing with a weak something in this conjugate. Should not differ by a factor of more than 10, which is what was asked earlier over there. And that's what I put up here. Okay. In any situation, it may, and then you would make that adjustment. For the purposes of the class, what I'm doing is I'm giving you a range so that on a test you don't have to worry about any more than that. But if you're actually applying this and you didn't have the proper system and you were trying to make a system that just worked for you, then you might want to go outside of this. Okay, so practically you can go outside of this for the purpose of the class. Here are the parameters to make it simple. Okay, so there's no ambiguity about what I'm asking on an exam.
Okay.
Okay. The other thing is I just mentioned, or I mentioned earlier, is the amount here. Okay. So I have both of these are 1-to-1, but you see the amount of the system is 0.5 and 0.5 versus 0.05 and 0.05. That's a tenfold difference. And I mentioned the amount also. That's just going to be relative to how much of the strong acid or base you're putting in. Right? If I'm putting more or something that's going to take this ratio too far down, because remember, the amount that I put in is going to adjust these ratios differently, right? If I put 0.1 molar, 0.01 in here, this is now going to become 0.06 and 0.04, something like that. And I put 0.01 here, this is now 0.499 versus 0.501. Those are big differences. You see that difference? And therefore the ratio at the end, when you're calculating the pH, is much, much greater, and it goes off of this, per se. So the amount that you're going to put in of the strong acid, strong base that you want neutralized has to be low enough so that the amount here doesn't change too much. The less change you have here overall, the higher the ratio, or the closer to the 1 that you're starting with, the lower the percent change of the pH. Okay? Hopefully you keep all those terms together, because that's saying a lot of things in sequence. One thing results in another and another and another. so here we're gonna add, okay, so we're gonna look at this now. We're gonna add the same amount of the strong base, 0.01 molar, or mole, into each one of those. Okay, of the first buffer, I have 0.5, so this is the higher concentration of the buffer system. So I'm adding 0.01 to 0.5 and 0.5, I'm getting 0.49 and 0.51. I'm just gonna plug that into the pH and I'm gonna get 5.02. So it went from 5 to 5.02, very small change. Because overall, the amount of base that I put in is very little compared to the concentrations of the buffer system. Okay. So this is just a change of 0.4%, very low. That's good. Now let's look at if I dilute the buffer system tenfold, so this is now gonna be 0.05 mole and 0.05 mole. Let's see what happens. I'm still keeping the same amount of strong base that I'm putting in. I now have this 0.04 and 0.06. I put those in here. I now have a 5.18 pH. Still neutralized it. I'm not that far off 5, but the percent change is 3.6 as opposed to 0.4. Big difference. So you could only imagine if I used more of this. Let's say I used 0.03 mole of this, how much further off that would be and how much greater of a change that would be, even though it's a 1-to-1 ratio when I start, which is just this. So the amount does matter in terms of concentration of both the conjugate acid and the weak acid and the conjugate base. Does that make sense? You can see that. You're just using more, and then you're adjusting the overall end concentration much greater, the ratio, which then changes the pH more or less, depending on how far out it went. Okay, so here are the differences here, so you can see that the amount matters of the conjugate. But then again, why would this not be always optimal to have more of it? So in other words, based on this, you would just automatically say, well, I should just always have more of the buffer system in terms of concentration. But why is that not always the case?
You're looking for a change. Sometimes you want to look for a change.
Sometimes you might want, yeah, just like we talked about before.
Slower change.
Maybe you want slower change. Maybe
Or
what I gave you an example last time of transcription and taking something and putting it in a buffer system so that when I put those other things in, they may come in automatically with some acid or base, and I want to keep the pH around the same.
Right.
But what if I have so much of those things? What if I have so much of what did I have in here? What was my system? This, whatever this weak acid is, and this conjugate base. Now, those things are interfering with what I want in my reaction because there's so much of it.
Nothing's gonna happen.
Right, now I don't get anything, I have the right pH system, but now I have something interfering with my actual experiment. I don't want that either. So I don't always want to have too much of these things in there. I want enough so that whatever I'm putting in doesn't have a huge change in the pH, which is optimal for whatever experiment I'm doing. So there's a lot more to think about than just, I want this perfect system like they're describing in the book. That's just a description based on not having any reaction going on, and just to get a feeling for what you're trying to accomplish, right? But now I'm saying take it in a real situation. You're putting something in, you're doing a reaction, and the amounts of these things now could interfere with that if they're too much. Even though I'll have a closer pH, the pH may not matter at that point, right? I have other things now interfering, like maybe I have in here, let's say I have acetate, right? So that acetic acid would be my weak acid. My conjugate base would be acetate. Maybe the acetate goes in and binds when I have too much of it to the polymerase, which then denatures it or keeps it from folding properly to react, as an example. The same way as if I change the pH too much, it doesn't fold properly. So I got to have a balance of all these things depending on what I'm doing in order to have a productive experiment. So just because these are the optimal conditions for not anything inside, you have to account once you're doing a reaction with these buffers what the optimal system is. And it also may be the reason why that, let's say acetate here, I don't want to use acetate even though that gives me my closest pKa to my pH. Because if I use another weak buffer acid, maybe HF, hydrofluoric acid, the F minus does not interact, let's say, with my polymerase, whereas the acetate does, but my pKa is maybe 4.5 on that, not 5.0 when I wanted 5.0. That's okay, I use that one, I make the adjustment here, so it's not a 1-to-1, so that overall will increase that pH closer to the 5 that I want.
You're saying adding a weak acid or base?
I'm saying
to
the
a
weak
buffer?
acid or base, you want to use also how, you got to know how that will affect whatever reaction you're putting in this buffer system.
Right.
It's not always just about the pH. It's also about the system, how much of that you use. So maybe if I just want to use the acetate and I know 0.05 is good enough, it's not going to interfere with my reaction, then I could use this amount. But if I use 0.5, it would interfere. So I'll take that as a loss of a little bit of pH, not to interfere with my reaction. So in other words, you have to make more decisions than the simple ones that I'm presenting here. It's not always so straightforward what you use in reality. But for the class, if I'm asking what's the optimal system, then you just simply state this kind of thing. Practically, that may not be the best system for you.
So then we can also add to a buffer system a weak acid or base as well to it, and we just have to do another ice chart to it to find the pH of it.
I mean, create a different buffer system that you want to put in, not add two buffer systems to the same.
Okay.
Which one?
Well,
I don't know
actually,
what
no,
you're
I
actually
want to,
saying.
like, I have my buffer system, I've made it.
Okay.
And I'm actually, instead of adding like NaOH, like a strong base or strong acid, I'm actually going to add a weak acid or strong base to it.
Well, you could presume that you wouldn't need a buffer system by putting in a weak acid or
weak-
weak base because it doesn't change enough,
A lot,
depending.
right.
Presumably, it's not going to change that much anyways, but you could check your Ka to make sure that, if you have a high Ka,
Right.
then that could be a problem. Because a
Okay.
high Ka, of course, would correlate with a strong acid or base where you're getting full dissociation.
Right.
Right. So
Stronger
it depends.
rating, stronger acid.
But if you, right, so it depends what kind of weak acid you would be putting in or whatever.
Nice.
And if you just had a weak acid that doesn't have a
middle,
high
that's
Ka,
not
then why do
gonna-
you even need a buffer system? It's not gonna change that much overall anyways, presumably. It
Exactly.
depends. It depends how much it would or wouldn't change.
Okay.
Right? And of course, if you did, you could always put in a little bit of its weak
Mhm.
or its conjugate to make
Right.
sure it doesn't change even more. So you
Correct.
just use itself as its own buffer system. You don't have to put it into one.
Nice.
So,
What is it called?
It would just
What
regulate
water
itself,
does, yeah.
self-regulation.
Uh-huh.
Okay, so those are the buffer ranges. Blah, 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 with everything we just said. I guess that's just like a review. So if I want to look at it this way, here's another way to look at it. The lowest pH, this would be the 0.1. If that's 0.1, that means the pKa minus 1 because it becomes a -1. And the highest, this would become a +1 here, and that would be pK +1. So these are the ranges of the pH that you want based on this idea here. That's all, right? This is just adding, this is just the log of 10 here, and this is the log of 0.1 here. And that's just the range. So this also means that if I had a pH of 5, then I wouldn't want the pKa to be, the pKa would be either the overall, if I had a pKa of 5, the pH, and I wanted the pH of 5, the range here would give me 4 and 6 in terms of the pH range between there. Okay. So let's see, maybe they'll show us that, yeah, here, right here, right? And that would just be, let's say, pK, I wanted 5, pKa is 5, so that's 5 minus 1 is 4, 5 plus 1 is 6, which is just this right here. That's all that's saying. And that's just based on the ratio of the buffer system. Okay. No, nothing new there, it's just another way to state it. Okay. Okay, let's take a look at this. Wow. So, what am I doing here? Which acid from the list below would you choose to create a buffer with a pH of 7.35? The one closest to that pH, right?
Yeah, 7.5.
These are nowhere near that, so they wouldn't be useful using that. Based on what we just said, what would be the maximum for this one? 4.34. And this one, 2.95, and this one, 4.74. None of those were even close to the pH.
Yeah.
So it wouldn't make sense to use those just by looking at it. But this one could go up to 8.54 or down to 6.54, all within the range, and is fairly close to the 7.35 to begin with. This would be the one that you would choose for your buffer system if those are the only 4 choices you had. Right, so let's say these are the only things you have in lab, and so you got to figure out which one to choose. You have this pKa information, that's the one you would choose for this. No big deal there, right? Go ahead.
What if it had like 6.54?
What would you choose? So let's say the HNO2, the one to the left of the HClO, was the pKa was 6.52, you said?
6.54.
6.5, whatever you want, 6.50, 6.55, whatever, 6.5, whatever. So this one is 6.5, whatever. Which one would you choose between these two if you wanted that pH?
HClO.
It's closer.
Still closer.
Still
Yeah.
closer. Okay.
Not within the range,
But if you had, what if now you had it, so in that case you could say I could use this one or this one, but this one is more ideal. But I gave you scenarios where maybe it wouldn't be.
Mm-hmm.
What if the reaction I wanted to put in that buffer, this conjugate would interfere with that interaction? Then I would use this because this is, I could still figure out a buffer that would fit that range.
Oh, it wouldn't damage it.
So I would default to the one that, another one that I could potentially use within a range that makes sense within a certain ratio. So then that's where those other questions, so on just what we're doing in this class, you would say this one for sure. But in actual practice or something that you're doing, you may want to use this one if it was 6 point something, 6.5 something, depending on how these things affect your actual reaction, whatever that may be, because it could be a variety of things, right? So definitely, for the purposes here, this is what you would say. But in reality, you would have to think beyond that and see what you're doing, and you become the expert in that field as you're doing research in that lab, whether you're in industry or academia. Does that make sense? In other words, I don't want to give you the impression that you got to always use whatever they say is optimal here, because that may not be the case, because there are a lot of other factors. So I'm just making sure that you're aware of that. Right? But for the purposes here, this would be the obvious, since I'm not saying it's in this particular reaction, and this would be inhibitory in that reaction. Okay. What mass of the oh, I like this. Okay. What mass of the corresponding sodium salt would you need to add 500 mils of a 0.1 molar acid solution to prepare this buffer? So I'm using this. So now I'm asking about the sodium salt that I want to put in here. So what's the sodium salt here? Na, sodium, ClO, right? That's the sodium salt. That's what it's saying. Right? You got to make sure that you can interpret that properly. Okay? That's my conjugate base to this weak acid. Okay, good. And it's saying what mass of that. So I'm starting with it as just a container in a laboratory, right? I have a container of a solid, and I'm just going to scoop some amount of that out. And what I'm asking is, how much of that do I scoop out to add 500 mils of a 0.1 molar acid solution to prepare this? What do I do?
Well, first we want to write your equation.
Okay.
And then
First, what are we doing here? Let's start with this. This is important. This is a test question. What am I doing? What are we trying to accomplish?
trying to get grams. Trying to get grams.
What are we really doing? Forget about I want a particular mass or something. What am I trying to do? I'm making a buffer. Thank you. That's important. I'm making a buffer. I'm not adding an acid to a buffer system here. That's what I'm making that distinction here. I'm making the buffer system with the acid. Remember, I told you there are two ways to make a buffer system. One is I could have the conjugate acid or base, or the weak acid and base, and I could make its and I could have its conjugate, and I put it together in a 1-to-1 ratio.
Right.
That was the first way. What's the other way I could make a buffer?
Salt and
If I have a weak acid and its conjugate base, I don't have the conjugate base, but I want to make that. What do I add? I add a strong base, right? If I have a weak base and a conjugate acid system, and I want to make the conjugate acid from the weak base, what do I add? Strong acid. But of course, I add a certain amount so that I end up with a good ratio closer to this, presumably, but somewhere in between this, right? The ratio. So I got to figure out how much to add. That's what I'm asking here, right? So let's start with that. You obviously know this. I could take this, and I want to know what here?
The ratio?
I already know my pH, and I already know my pK, right?
Your ratio?
So I should point out that I want to create this buffer at 7.35. That hasn't changed, and I'm using that as my pKa.
Okay.
So therefore, what must I figure out here? This is my base, this is my acid, right?
Okay.
In my buffer system.
From the concentration of the acid.
So I'm trying to figure out
Of the base.
how much sodium salt, this here, would I add to this?
Right.
So I gave you two methods to making a buffer. I could add the salt or the conjugate with whatever I'm starting with. Or alternatively, I could add a strong acid or base to neutralize some of whatever I started with the weak acid or base. Which one am I using here?
You're adding a strong.
Well,
You're adding a strong.
that's be strong base because that's a big acid.
So I'm saying that I want to know how much of this here to add to that there, right? So that means in this here, I already know what I have here, right? It's right here. So I need to figure out how much of this I have to add. From here, if I know the total volume, since I'm adding, you're going to assume that I'm adding a solid, that's the total volume, right? This is going to outweigh the, if I have the total volume, can I then figure out the moles of this that I need? And from the moles, can I figure out the mass? Yeah. So what do? I put this whole thing in. This thing is equal to what? If I look here, I'm trying to find this here, basically, right? So if I use this, this is 7.54. This is what, what was it? 3.5?
3.5.
So 7.35 minus the 7.54 leaves me with this. This is just rearranged. Is that clear?
Right.
Okay. This minus this gives me a negative 0.19. Now can I take the anti-log of both sides?
Yeah.
Okay, let's take the anti-log of both sides.
0.65?
0.65, we're good so far?
Yeah.
Okay. Now can I move this up here?
Yes.
Yep, I could do that. And now what do I have left? I'm solving for this. Do I know what this is?
Yeah.
Okay. So that's just maybe I didn't do that. 0.65 times, this is the molarity of the acid, 0.10. 0.10 times 0.65 is 0.065, right? Okay. And now I could figure out this based on if this is my molarity. What do? What's my volume? 500 mils. And what else would I need to know here? Molar mass of this, right? Okay, good. So there's my volume times the molarity. I now get rid of my liters. I multiply by the grams per mole of the molar mass of the sodium ClO, which I get as 74.45 grams per mole. And that gives me, I would need 2.4 grams of this added to the 500 mils of the 0.10 molar acid in order to make this buffer system ideal. Okay. We're going to do a couple, go ahead.
The 0.65, 0.065.
Oh, so this here is equal to, this is equal to this times this, right? If I move this over. And this is here. So 0.1 times 0.65 is the 0.065. Is that okay? Maybe, maybe not. Let's do a couple more. Okay. Now, this specifically told you I want to use all this. I could have also said, what if I wanted to just this is the amount I had, does not mean that that's the amount I need to use, right? How would I determine in a lab how much I would actually use?
pH.
Well, wouldn't it depend on how much you need
Yeah.
of the buffer for whatever you're using it for? Right? If I only need 2 milliliters, am I going to use all 500 mils here? That's what I'm asking. No. Why? Because it's going to go bad at some point. I just wasted it.
Yeah, too much.
How much would you use if I wanted to make 2 mils? If I needed to use 2 mils?
Probably.
Maybe 10, 5, something more than the 2, obviously.
Yeah.
But I would want to save that other amount so that if I needed to make some more or something else or some other ratio of the buffer, maybe I wanted to make a couple different ratios here. Right? Because I don't know what the best buffer condition is for my reaction. And each reaction is going to take, say, 1.5 mils. So I'm going to make 2 mils for each reaction. So then I would do a titration of different amounts. So then maybe I'm going to make a bunch of 2 mil different buffer ratios here. And then I'm going to run my reaction into all of those, and I'm going to see which one gives me the best results. This is exactly how you set up the optimal conditions for whatever it is you're looking for. Does that make sense? And you would do that with temperature, with time, with pH, and anything else that you're using. Maybe in the example I gave you with transcription, polymerase uses magnesium. So maybe I do a titration with magnesium. And then I know overall the optimal amount of pH that I want, the optimal amount of magnesium I want, the optimal time frame I want to use, and the optimal temperature. So now I put all those things together, and that's how I do my experiment from here on out. Now I could make mutations in my protein or my DNA, and then through that with the regular wild type, I compare those under those optimal conditions. And I see which one go up, go down, etc. And then I could say these things have an effect. This is how the mechanism works. The DNA melts because this particular piece, the amino acid on the protein, is defective. When it's there, I get the best melting. When this base on the DNA is not there, or I change it from a thymine, let's say, to GATC, so a G to say a T, right? Then it's not optimal anymore. It melts, and so then you'll look at different promoters, and you'll say, well, this one has a T there, this one has a G there. Why is that? And that's because one thing the cell may want to control one thing more than the other. But I wouldn't know any of that data or any of that information had I not done all these titrations to set the optimal buffer for that reaction, which may be different than the optimal buffer for any other reaction. So when you put together the buffers, a lot of times you're just trying to mimic, say, the environment it comes out of, but then you make adjustments as that is the starting point to see how it goes up or down relatively. Because in the cell, you don't always have optimal conditions to do things because you want that regulation. Because what happens in a cell where you have a lack of regulation of something? Cancer. Absolutely. Unregulated. Cancer isn't because there's a mutation that blocks something from being made, then the cell dies, no big deal. Right? The cancer comes because the cell is a mutation in the cell where now you have constitutively active proteins and enzymes that keep making and expanding. So instead of the cell differentiating, what is it doing? It's just multiplying.
Yeah.
And that's exactly why you don't want to have all these that I'm describing here optimal conditions all the time. So then when you're testing to see where the changes are, what matters, you're testing for things based on what you start with, which is the cell environment, and you figure out what the optimal conditions are, and then you can figure out which things are having the greatest effect in that process. This is exactly how you do research of something that you don't know how it works, right? So hopefully that puts these buffer systems a little bit more clear, is that's why I'm saying this is just representing the optimal, which generally is not what you usually want, right, in a cell or some biological organism. Okay, so here, which solution is the most effective buffer looking at these? Let's just start with this. One effective or not effective? If it is, why? If not, why?
It's not.
It's not. It has a strong acid. That should be obvious. This is a great test question. This is your multiple choice test question right here for this set, for part of this chapter. That's clearly a no. You should, if you can't identify real quickly you have a strong acid there, you can't make a buffer system with a strong acid. Doesn't make sense.
Yeah. Let's see.
Right? Okay, so then let's go to B. I'm mixing 100 mil of HF and 200 mil of NAF, and they're both the same concentrations.
But not the same milliliters, not
No.
the same amounts.
I'm going to end up with more of one than the other by double.
Yeah.
Okay, so I'm going to be at one of these ends here, right?
Right.
Okay. So that could be. Let's see what the others say. Here I have solution prepared 150 mils of a 0.1 and 150 mils of a 0.1 mole here.
Yeah.
That's not bad, right?
Yeah.
I'm going to have the same amounts of each, so I'm going to have something close to this ratio here. So right now I'm going to say that. What do I have here too? So this is just the opposite way. So I'm going to have one here, one here, one here. I clearly want that. That is C. So I look here. Oh, here's my ratio thing that we're talking about, this kind of thing. Glad that was still up. And that would be the one we want. And that's clearly no good because you don't have any system there at all if you have a strong acid or a strong base to start with. So this should be, I mean, and how long should that take you to figure out on an exam?
Seconds.
A little more than 10 seconds, right? So that's what so knowing certain things, you would never even need to use your cheat sheet on something like this, right? These are just things you should know at this point, and then you just apply them accordingly.
Can you explain the last one?
Now what?
Can you explain D again?
B?
The D.
D. Well, D is just this, essentially,
It's the
right?
opposite of the ratio.
The ratio. So I'm looking here at the ratio. And here, I'm using 200 mils of a 0.1, and here I'm using 100 mils of a 0.1. That make sense? So I'm going to have the ratio. I could actually use this, but this wouldn't be better than this without knowing what my reaction is going to be. If I knew my reaction, I may actually want this ratio, as I've described multiple times now, to show more practicality
Or B.
to making these systems.
Or B.
Yeah, or B in some, but just without knowing what the reaction is, this is clearly going to be the best one because my ratio is a 1-to-1. Okay.
Depending on what you have available, pKa availability as well.
And I guess one of the things to that question is, just to make sure this is clear, because now that I'm thinking about this question, some of you may have just saw that, hey, it's 0.1 and 0.1, 0.1 and 0.1, so it's automatically 1. But this is, if I find the moles of this and the moles of that, and then I redivide by the total volume, that's where the ratio is now different, right? Okay, and that came up earlier from the questions over here. So maybe that's a consistent theme here to be careful about. If I take 0.1 times 100, how many millimole do I have on that?
0.1.
And then if I take 200 times 0.1, how many
10.
millimole do I have this?
20, yeah.
And then I divide by what to get the molarity again? The total, which is 300. Ratio is different now. If I just said, oh, I have 0.1 and 0.1, then they all look like it's a 1-to-1 ratio. Is that what was confusing?
Yeah, I got it.
Okay. So that I remember the questions earlier over here. Jenna and Dieter had these questions, so I want to make sure that that's now clear. So that's why it would be different here. Okay, we're here, though, it's going to end up the same. 0.1, 0.1, 150, you get the same, and then you just divide each one. The ratio is going to stay the same. It's going to stay 1-to-1. Okay. Okay. This is just stuff we've already done. Okay. So I guess there are just some more examples. So let's get through some of these examples. What is the P? This is basically like a. Let's just assume we're like on a test, and we're going to look at some questions that you would get on an exam. Okay. What is the P? Everything else you already know at this point. Now it's just applying everything we learned in the earlier parts of this chapter to this. So what is the pH of a buffer made by mixing 3 liters of a 0.02 molar benzoic acid with 1 liter of a 0.05 molar sodium benzoate? Ka benzoic acid is this. Okay, this is a pretty simple problem, right? What do I do here?
Get the molarity.
I get the moles of each. and then I go back to the molarity of each. No big deal there. Why do I have to do that?
Because you're adding them to the volume.
Because the volumes change. I'm adding them individually to the end.
Mm-hmm.
Okay, so I have different total concentrations. Once I have that, I get pK of this, and I could easily put that into what equation? So what equation should definitely be on your cheat sheet? Henderson-Hasselbalch. And how many of you are actually going to use it? Hopefully 0, because it should be so obvious how to use it that you don't have to waste time looking at your cheat sheet, which is exactly what you should be doing, because the cheat sheet is only supposed to make you feel comfortable. If you're spending a bunch of time trying to figure out stuff off your cheat sheet, you're probably not in a good state. Because the cheat sheet not only will not help you, but now you're wasting time. Instead of trying to solve problems, you're trying to figure out where an equation is, and then you've got to figure out how to solve it with that equation, if you even need that equation. Right? You see the complication there. Don't write those cheat sheets. When you're writing those cheat sheets, those should really just be reinforcing the concept so that you probably don't need it, but sitting there makes you feel good. Right? The same way Snoopy and his blanket feel good. Right? You never see them dissociated. They're always together. Okay? So keep that in mind when you're looking at this. Okay, so let's see. Calculate the molarities. 3 molar of this gives me moles, and then I divide by the total. 3 and 1 is 4. There's my new molarity of the acid. Here's my molarity of the conjugate base. Okay, nobody should have a problem with this, right? Now I just use the Henderson-Hasselbalch. The only thing, if I'm on an exam and I'm looking at the Henderson-Hasselbalch, the only thing I may want to double check is this is the base, this is the acid. Beyond that, and you should already know that, but maybe you get a little bit uptight in the tense situation and you say, okay, I just want to double check. The base is here and the acid's there. Nothing more than that, right? Okay. pKa you solve for, so this is just this. You take the negative log of that. That gives me 4.2. I put these numbers in here from the concentrations, and then I take this divided by this, take the log of that, add it to the 4.20, and I end up with 4.12. That's my pH. And that's a classic pH problem that you'll have on the exam. No big deal. That should be pretty easy. Peter?
Here they use 0.0125, but the initial molarity was 0.025. Go backwards.
Here?
They have a different.
Whatever it is. If it's 0.1, if this is wrong, then use whatever you get here, that's what you use. I don't have a calculator in front of me, but if this is off, then use whatever it is you get. Okay. Okay, let's go to a little bit more challenging problem. So a buffer is prepared by adding 115 mils of a 0.3 molar ammonia to 145 mils of a 0.15 molar ammonium nitrate. What is the pH of the final solution here? It's kind of the same thing, actually. What's different, though?
It's just a base.
It's a base. That's why I have Kb. So I could do, okay, in the past, I deviated a little bit this semester from this, but in the past, you just solve for the pH, using the pH from the Henderson-Hasselbalch, right? So that means I just have to convert the Kb to what? Ka. Kw over Kb gives me Ka. But this year I actually showed you guys something different. I could solve for the POH directly, right? I could just simply take I can get from the Kb the pKb, and then in the Henderson-Hasselbalch I'm just flipping now the acids on top and the bases on the bottom. I can do either way. It doesn't really matter. You're going to get the same answer either way. Okay? In both situations, I need to figure out the new concentrations here because I'm mixing 115 and 145. So I do that first. So my concentration of ammonia, assuming this calculation is right in the calculator, is this. And then of the ammonium chloride here, or this should really be ammonium nitrate, doesn't really matter. It's just the base here because those are separated. Gives me this. Right. Okay, and I'm assuming they'll just show you finding the Ka. That's my assumption. I just want to reinforce it. You don't have to do that. You could just find the POH and then you take 14 minus the POH to get the pH. Right? Okay. So yeah, they're going to do this. So that means I have to convert this to Ka. So it's just 1.0 times 10 to the minus 14 divided by that. And if I do that, that gives me 9.25, which should make sense because the pKa should be higher than, and then here are my calculation. Now, all I'm saying is I could have taken the pK of this directly, and that would be the pKb. And then I could have flipped this here. That would have given me the pOH. And then I take 14 minus that. Okay. Or alternatively, I take the Kw divided by that to get the Ka. That's what I did here. And I end up with 9.45. The first thing I want to evaluate, though, since this is a base system, right? So I'm starting with a weak base and its conjugate acid. The overall should be higher or lower than 7 in terms of the pH.
Higher.
When especially since I'm starting, do you remember how, do you guys recall, I think it was this chapter, when we looked at things like Kb, and we looked at things just of concentration of hydroxide and hydronium ion, remember that? And when I had 1.0 times 10 to the minus 7 of each, that was neutral.
Yeah.
When one of them was higher than the other, in terms of the concentration, that meant it favored that side, right? So it favored the hydroxide or the base, therefore higher than 7, if it was greater than 1.0 times 10 to the minus 7 or less. So you could also get in and just say, well, what are my concentrations of these things, which one's higher? Right, and that should tell you that that's gonna go higher, because I could change the ratio here, and then potentially that would go a little lower than 7. You can't always just look at it a certain way, but you could also look at the Kb. What does the Kb mean again?
The Kb of the equilibrium of the base.
And so the higher the Kb, what?
The stronger the base.
Stronger the base, more dissociation.
Right.
Okay, so then so you can think about this in a lot of different ways to kind of gauge what you would expect. Should this be more basic or more acidic as a solution? Okay. I probably won't give you something that challenging. Oh, now they're going to throw in this after the fact. Interesting. Okay, here's your Kw divided by Kb, and then you take you get the K, and then you take the negative log of that, and that's what this is right here. That was really awkward. All right. Okay, so now let's do this. Let's do another one here, or maybe do we need to do another one? This is the same thing, right? You guys can do this one at home.
Yeah.
It's exactly the same as the last two. Okay, good. Yeah. Oh, maybe not. Okay. So what do I have different here? I have the acetic acid. What is different here? Okay, so I had this discussion already multiple times today. What's different about the first two in this one?
Strong base.
I'm creating the buffer system using the weak acid and a strong base, not its conjugate base. So I'm creating the conjugate base from the weak acid. Everybody see that? Once again, I talked about this last time, and I talked about it a couple times today. So the last couple examples, this equation here wasn't up because I already had a certain amount of this and a certain amount of this.
Right.
Right? Now I'm creating a certain amount of this from this using a strong base. So I sure don't want to neutralize all of that. I want to do what to this? Cut it in half, ideally, right?
Yeah.
Right. Okay, so let's see what we start with. We're starting with 400 mils of a 0.2 molar of this and 100 mils of this. So now I got to figure out the moles of this, or millimole, the moles of this. Then I go through my ice initial change end, because this is an end point here, to see how much of this I have left from this and how much of that I have left. And then I put those back into their concentration form by dividing, what do I have here, 100 mil, by dividing by 400 mil, or half a liter.
Mm-hmm.
And then I could use my Henderson-Hasselbalch equation. But I'm not given the amount of this yet. And the amount of this is going to change because of the amount I'm putting in here. I'm now making the buffer system starting with the conjugate acid. I'm not using, or the weak acid, I'm not using the weak acid and its conjugate base to make this. I'm using the weak acid and a strong base to cut some of that weak acid down into its conjugate base. Okay, I want to make that clear. That's all this is going to say here. You guys have this in your notes, by the way? No, that's already in your notes. Oh, good.
Half
Okay,
filled.
cool.
Yeah.
Okay. Okay, so let's do that. So first, the millimole of acetic acid is given at 80 millimole, and the millimole of the sodium hydroxide, 30 millimole. I divide that now by the half liter to get back to the concentrations of, this is going to take away how much of this? 30, so what am I gonna have left here? 50? How much of the conjugate will I have? 30. Right, so then I use those numbers, 50 and 30, divided by the half liter. That gives me my concentration of what's left of the weak acid, and now its conjugate base. Okay. Okay.
Wait, can you say that one?
Yeah. I'm using 80 millimole of this and 30 millimole of that. This is a strong base. This is all going to be used up. So I'm going to use up 80 minus 30 is 50. And then what am I going to have left of the conjugate base of this?
Have
30. And then those are amounts, so then I divide that by the total volume, which is half a liter. And those are my new concentrations of my weak acid and its conjugate base. Okay. And it looks like I'm going to do that here. Okay, so here's what I'm starting with, right? Change, this is going to be minus 30 plus 30. That's going to leave me with 50, 0, and 30. So this is basically that right there. What I really pointed out there was, you know, when you're familiar with this and if you've done a couple problems, you could do that in your head. You don't actually have to draw this chart. That's sort of what I'm showing you there, right? Okay. You could do the chart.
Yeah.
You could imagine how much longer it takes you to do a chart on an exam than if you understand this. This is pretty straightforward, right? Unless I give you some complicated numbers, maybe. This is like 80 minus 30, that's 50. Right. Okay. So now I divide by the total volume, which is 500 mils.
You
So that gives me 0.1 mole of the acetic acid and 0.060 molar of the sodium acetate. So then I go ahead and now I just use my Henderson-Hasselbalch equation. Now it's all the same. I know my pKa. This one here is my base, so that's this one. So 0.06 divided by 0.10. That gives me 4.52. So that's my pH of this buffer system. Now on a test, I could also do what here? I could also then say, make your buffer system. Now I'm going to add in some strong acid or strong base. What is my final pH? Right? I could make it into a two-part system. First, you got to figure out what your buffer system is. And then the second part would be, now I'm going to add an acid to it, or I'm going to add a strong base to it. What is the new pH? That wouldn't be all that challenging for you at this point. Kind of like doing, you know, same thing, similar here, over and over. But it just, what would be the value of a question like that is, well, now you're figuring out how to make the buffer and what it means, and then adding something to it, what the changes would occur from it.
And you may give us the KB instead of the Ka.
Yeah, I could make KB into the Ka, and I could put in acid instead of base, or whatever. Okay. Okay, good. This is a simpler problem. Since we're out of time, I really want to I thought we'd finish this part of the chapter by now. But I think giving you the practical examples of things is just as important, so that you don't get caught thinking that it's all one way. That's
We have like this and two other questions, and then we're on to the acid-base titration.
okay, good. I think you'll like the, okay. So let's just do these questions and then we'll wrap it up for today. And we'll get into the titrations tomorrow. Or
4.5 was the answer?
What?
4.52?
The last one?
Ah.
Yeah.
Okay.
4.52?
Nice.
I heard another something asked back here.
No, the next example, we had pretty much the same question
This one.
Yes.
Which solution is,
Well, it's a little bit different. It's a tiny bit different.
how's it different? This is good.
Um,
It looks similar.
they're not.
All of them have strong bases.
You have like 150 and 100 versus.
The last question, I gave you exactly the thing I've brought up now multiple times today, right? I gave you the weak acid and its conjugate base.
Right.
This time, I'm giving you the weak acid and a strong base, because you're gonna now make, just like we did in the last problem, its conjugate. So you don't want to use it all up. So let's start with the first one. That's almost exact. That's hard. If anybody gave me that, I'd say you probably weren't sitting in this class, right? If anybody chose A, you got a strong acid and a strong base, and there's no way that's going to make any kind of a buffer.
It's the same molarity,
Right?
yeah, so,
That should be blatantly obvious.
yeah.
Otherwise, we've all wasted our time in here. The next one here, you can see these are all weak acids. So in this case, I can just look at that group. And
So
now I'm
B.
putting in strong bases, so I want to cut this in half ideally.
Yeah.
Mhm.
So if I have 200 mils of this and I use 100 mils of that, and
That's
there-
the
yeah,
one.
that looks like it's probably pretty good,
That's the one, yeah.
right?
See what
But let's
happens.
just see what else real quickly, since it won't take long. 150 mils of this and 150, the moles are going to cancel. I'm going to end up with nothing left here.
Nothing left from the
So it won't
acid.
be, it won't be a buffer system here, it'll just be a neutral system.
Right.
This will just neutralize. And this one here, I'll end up with a really strong basic
Base,
system.
yeah.
So I won't have any buffer system again, it will just be really basic. But here, I'll cut half of that down, and that will leave me with half of this and half of the conjugate base.
So, for example, just say you had a strong acid and a weak base, it would be the exact opposite?
Yes, absolutely. So the question is, if you had a strong acid and a weak base, you do the same thing to make that system. Okay, and, oh good, we're right. Got to double check that, you never know, right? Okay, now let's finish this off. This is the last question you said?
There's
Two more.
Two more, okay, let me take a quick look, see if we need to do this in class. Buffer is prepared by dissolving this and this in enough water to make blah, blah, blah. How many grams of this must be added to 4.2 grams of this to prepare this buffer with a pH, okay, blah, blah, blah. All right, what's happening here? What is this and what is this? What is this? It's a weak base. It's a question you just asked, basically.
Mhm.
Right? Except for it's not said in that question. This is a weak base. This is its conjugate acid. Right? First thing you have to recognize. If you
Oh,
don't
good.
recognize that, why? I have anything with a nitrogen or amine, you can
Mhm.
call it. Let's just say nitrogen to make it simple.
So
It's going to be a
base.
weak base.
Right.
Unless what? So think of NH3. That would be your classic, right?
Yeah.
Mhm.
Then when I add another hydrogen to it, what do I have? Ammonia. So now it can act as what? An acid. The same thing some of you missed on that last exam, right? When you circled those things. Just because it had the N, if all the N's are occupied and there's a plus there, then it's going to get rid of an H because it doesn't have the lone pair.
It's an
But
acid.
without that other H, there's a lone pair there. That's what's acting as a base
Base.
because it's pulling off a hydrogen off something, leaving the hydroxide behind.
Mhm.
So then you could view this as NHHH. There are two of those. That's the same thing as NH3 plus, right? Or just NH3, I'm sorry. So that's the same thing as this. So let's make sure we're clear on this. This is just NH, let's call that R group and R group. This here, same thing as if I had NH3, each of these I just pretend is an H. This lone pair now can pull off an H off of the water, leaving this behind, hence base. Okay? Okay. Sometimes changing those, and remember how I did that trick of changing into R groups here? That's all I'm saying, that each CH3 is an R group. Now, I add another H to it, which is what I just did here, and I don't have that lone pair anymore.
Right.
I now have this, and I have an overall charge of the plus, so then I mix that, in this case, with the Cl minus, and that's what you're now looking at as
So
its conjugate acid.
So the H actually was brought from HCl.
This is the weak
Oh, not
base,
HCl.
and this is its conjugate acid. Because now this can go off, conjugate acid.
Yeah.
Okay, so make sure you can identify. Now, what do I do here from this point on? I want enough water to make this, so I put this together. Can I put this together, let's say, into, remember we did something kind of like this already, right? How would I do this? Put it in the Henderson-Hasselbalch, and I can then figure out the ratio of the A minus to the HA.
Yeah.
And then do I have any information on some of that stuff? I could then figure
Yeah.
out, I have to start with 4.2 grams, so I could figure out how much, I get the moles of that by using the molar mass of this.
That's the HA.
And then I have the total volume already here. I divide that by the total volume. I have my concentration, which would allow me to figure out the concentration of the other one, multiply by the volume to get the moles, take the molar mass of that thing to get its mass. Very similar to a problem we've already done. So I'll quickly throw this up. Sure. So all I did here was identify these things for you, just in case you don't know. And here I don't need to do this, but if I wanted to use the pH instead of the POH, it's up to you. Whatever's easiest. So if I want to use the pH, not the POH, then I'm using the, I got to convert to the Ka. pKa is that. So here, I'm putting the base here and the conjugate. This is, once again, you could just call this the base and the acid, doesn't matter. Right, don't get confused by that. If I'm using the pH form of this, this is always the base, this is always the acid. Doesn't matter which one's conjugate or not, okay? But you had to identify that, that's what I showed you here. Okay, so then I put in, so but this is my pH, there's my pKa. Subtract that, right, I'm subtracting that through the pH equals the pKa plus this. I move this over, this minus that gives me negative 0.27. What do I do here? Anti-log, same thing we did before. Anti-log of that gives me this. I move this one over. Or which one am I trying to solve for here? Which one do I already know? I don't have my... I'm trying to solve for B?
Your base.
Oh, so I already have the mass of this one?
Right.
Okay, so I move this over. Wait, which one do I have my mass for?
You have the mass of your, yeah.
I have my mass for this or this?
For that one, the bottom one.
This one.
Yeah.
Okay, so I now take 4.2 grams B times the 45.1 gram of, I guess that's whichever, that's this one here, right? So
Right.
that's 12 plus, you know, or 12, 15 times 2 is 30, 31 plus 14. So, you know, 45 or whatever, that's what I get here. And then I go ahead and I go from moles, here's my volume, and there's my molarity. I plug this back into that equation here. Okay, solving for pH plus now. And now I can figure out my concentration here. I divide by this, or I multiply by this. Which one? If I have the concentration here.
Oh, divide.
Multiply. That
Oh,
gives
to
me
get
my
the-
moles.
Okay.
I get the molar mass of this.
Yeah.
I multiply the moles by the molar mass. What do I end up with?
Mass.
Mass. And that's what I'm trying to solve for, right? So this times this gives me 14 grams of that. This is almost identical to the problem we did earlier, right? But it asked something a little bit more challenging. Instead of giving you the concentration of the first one, I gave you the mass of the first one. So you had to determine the concentration. I gave you the mass and the volume.
Mm-hmm.
So the first one I gave you the concentration and the volume.
And you gave me the
This
mass
time I gave you the mass
of the
and the
base.
volume. That's the only difference between this problem and the earlier one. So that means there are extra steps to figure out the molarity. And lastly, instead of doing, I want you to do this at home. You were instructed to prepare 100 ml a buffer solution with the pH of this. You have this available and you have this available. Develop a plan to prepare this buffer. There's no right answer. The one thing I will say is, as I've talked about before, you don't want to use everything you have. There's also going to be one that's going to be somewhat limiting. So I would probably start to see, this is probably going to be limiting. Let's start with that. And then I wouldn't use the full 5 grams. 3 grams, 4 grams, 3.5 grams, whatever, okay? From that, you could figure out what the concentration is, and therefore how much of this one to use, using very similar rationale to the last problem, okay? And with that then, depending on what amount you use, let me just show you what they use here, so that if you wanted to match, so they're going to use 4 grams of theirs. So why don't you just use 4 grams there? But the idea of that problem was to design it so that you use as much as you want. But if you want to then check your answer, use the 4 grams. If you want to use 3 grams, then you would end up using less of what the other thing. Doesn't really matter. 3.5, use whatever you want, okay?
Mm-hmm.
Okay. That being said, I'll see you guys on Thursday as I move through there to make sure that you can't see it.